topological spaces, there is a natural question whether one can form new topological spaces out of the given ones. And one such construction is that of product topology. So, let us explore that. And see what goes on when we try to define a product on topological spaces. So, before we move on to the actual definition of product topology, let us see what is meant by an arbitrary product of sets. So, let X be a set and let J be an index set. So, X to the J is by definition set of all functions from J to X. In fact, this function is determined as follows: if alpha is in J, that is an index set, this implies that f at alpha is going to belong to X, and hence we shall write f as f alpha as alpha varies over J, and we call elements of J as coordinates of f. So, what is x raised to j? This is by definition all functions from j to x, which can also be thought of as all j tuples. X raised to j can also be thought of as all j tuples of elements of x. Now, we will generalize this as follows. We have the definition of arbitrary product of sets. So, let X alpha be a family of topological spaces which are in particular sets. Then let product X alpha as alpha varies over J be, as before, set of all functions from J into now the union of all X alpha as alpha varies over J, and we impose the following condition, namely when you evaluate f at alpha, evaluate the function at a coordinate alpha, then the answer should precisely belong to X alpha. You will see that when you have finite products of sets, when you have a product of finitely many sets x1, x2, xn, then the Cartesian product x1 cross x2 cross xn corresponds precisely to all functions f from the set 1 to up to n to the union of xi's such that fi belongs to xi. This is exactly a generalization of that. Now, we have the following definition of two kinds of topologies which are available on products of sets. The first one is called as the box topology, and the name will be illustrated soon. So, the box topology on the product X alpha, where alpha varies over J, is the topology defined in terms of basis elements on that set which has as basis all sets of the form product u alpha as alpha varies over J, and u alpha is a subset of x alpha for every alpha in J. Moreover, U alpha is also open subset of x alpha. So, the box topology is determined by a basis consisting of products of open sets, each coming from the corresponding open set. For example, if you have only two topological spaces, say x1 and x2, let us see what this box topology is on x1 cross x2. So, a typical basis element will be of the type u1 cross u2, where each ui is a subset of the corresponding xi and it is open in that xi. An important word of caution needs to be said here. Note that elements of the type above u1 cross u2 are only basis elements. In general, an open subset, so the caution says open subsets of x1 cross x2 need not be of the type u1 cross u2, because you are taking the topology generated by a basis, and we have seen in the previous videos that topology generated by a basis consists of unions of basis elements. For example, to be more concrete, let us take x1 to be R to be x2 with the standard topology. Now observe that an L-shaped diagram in which you do not allow the sides to come in is not a basis element, because it cannot be written as a cross of two basis elements. In fact, it is a union of two rectangles, as you shall see, and hence in particular it is not a basis element, but it is a union of basis elements. So, this is one place where one has to be very careful when one talks about product in topological spaces. There is another kind of natural topology which is induced using again basis elements, and this is called as the product topology. So, the product topology on the product of topological spaces indexed by a set J has as basis all sets of the form product u alpha, alpha varies over J, where u alpha are subsets, open subsets of x alpha. U alpha is equal to x alpha except at finitely many alpha. And it is this second condition that u alpha becomes the whole space except at finitely many alpha is going to distinguish between the two topologies. So, let us see that via pictures. So, let us compare the box topology with the product topology. For example, in R2, a basis for the box topology consists of u1 cross u2, where ui are open inside each of the xi's, that is in this case inside R. So, typical element of the box topology here looks like this. Of course, you are allowed to vary the u alpha as you like. So, in fact, we can see that you can take this open set along the y axis to be whole of the y axis, because y axis is open in itself. So, what you actually get is that you get a box when you consider u1 cross u2 in the box topology, hence the name. If you try to draw the pictures in the product topology, you will see that u alpha has to be x alpha, that is u1 has to be r, or u2 has to be r, or both u1 u2 can be arbitrary. So, a typical possible basis element is of the type a strip like this. The two topologies actually really distinguish themselves from each other when the indexing set is not finite, and details of this will be outlined in the notes. However, since everything has been described in terms of the basis, we also have the following nice and useful theorem whose details are quite easy to write down. So, we will only state the theorem here. Suppose each topological space x alpha tau alpha has basis b alpha, then we can actually extract a basis for product x alpha out of this in the box as well as product topologies. So, then product b alpha as alpha varies over j is a basis for product x alpha as alpha varies over j in the box topology. This is an easy exercise. Similarly, you can prove that product b alpha as alpha varies over j is a basis for product x alpha alpha in j in the product topology, provided where you allow b alpha to be x alpha except at finitely many alpha. Thus, product topologies can be very naturally described using basis, and we will use these product topologies to construct an example of a topological space which is not metrizable, that is, its topology cannot come from a metric. This is actually a very concrete example showing the advantage of studying abstract topological spaces over metric spaces, though many a times the properties of topological spaces are very much similar to metric spaces. We will in this set of lectures on product spaces explicitly construct the example and show